In this lecture, we will discuss about torque on an electric dipole in uniform electric field. We have discussed in previous classes what is electric dipole. Whenever we keep this electric dipole in an electric field, it experiences a torque. We have developed many applications of this torque. As due to this torque, you can move the dipoles and may have many applications. We will discuss the details here. In this lecture, we will talk about what is torque. We will define the torque, especially in reference to electric fields. Then an expression for torque we will discuss. We will also discuss energy, potential energy, and finally the significance of this for us. Before learning to the torque on dipole, first we will talk about what is torque. The torque is the measure of force that causes an object to rotate about an axis. This rotation is possible when we have two forces in opposite direction. Whenever anything rotates about an axis, it's called torque. Torque is a vector quantity and its direction depends on direction of force on the axis. The magnitude of the torque can be written as Fr sin theta. R is the length of the arm and theta is the angle between moment of arm and vector. If you want to check this, you can write like this. Suppose there is a force in this direction is F. Similarly, force in opposite direction is also F. So this will try to rotate, and this R is basically this distance. And this is the theta. So whenever you want to take the distance, you will take this distance. From here we can calculate the value of tau. Yes, of course, the tau has vector notation. We know the electric dipole. It is a pair of electric charge with an equivalent magnitude but opposite charges, separated by a distance d. So we have already discussed this in the previous lecture also. Suppose you have two charges separated by very small distance d, then they form dipole. The electric dipole for this is defined as the product of magnitude of the charges and the distance between them. The electric dipole is a vector having a defined direction from the negative charge to positive charge. Yes, we have already discussed this in previous class. So the moment can be written as P is equal to QD. If we place this in electric field, we have shown here the electric field is from left to right. Then there will be a force exists. As we know, the electric field means this is positive direction and this is negative. So the dipole negative side charge will move towards the left and this towards the right, and the top. Now consider a dipole with charge q and minus q as shown in the figure. Forming a dipole, since they are at a distance d away from each other, let it be placed in a uniform electric field such that the axis of dipole form an angle theta with the electric field. The force on the charges can be done as F is equal to QE or F is equal to minus QE. Actually, this should be like this. This should be on subscript, and this can also be done as F. Similarly, for F minus, you can use this, and this can also be. Now you have both F minus and F plus. The components of force perpendicular to the dipoles are these two components, plus QE sin theta and plus minus QE sin theta. This plus sign and minus sign should be in the foot of this F. Since the both forces magnitudes are equal and separated by distance d, the torque can be applied here. The torque can be done as force into distance separating the force. Or you can use tau is equal to force means QE sin theta and force is the separating force is d, distance is d. As we know, the dipole moment is qt, E is equal to qt. The direction of dipole moment is from the positive to negative. It can be seen from the above equation, and the torque is the product of dipole moment and electric field. This can also be written as, that's why tau is equal to P cross E. The torque is in the clockwise direction in the above figure if the direction of electric field is positive. Since it is clockwise direction, it should be negative, and this is there PE cos theta. For opposite direction, it can also be calculated as tau is equal to P cross E. Yes, you can hide these maybe like this. Or it can also be improved as we take the magnitude of is equal to P cross E. So we can summarize that the measure of force that causes an object to rotate, this is known as torque. Torque is responsible for rotation. A pair of electric field charges with an equal magnitude but opposite charges separated by a distance called dipole. Since the force magnitude are equal and separated by distance d, the torque is given by torque is equal to force into displacement. Distance separated force, and torque is equal to PE sin theta if the field is uniform. The torque produced on an electric dipole by an electric field can be expressed as vector product with direction given by right hand rule. So this is all about torque. We have assumed a dipole, so we have to take care this tau is equal to P cross E. This torque is zero. At, there are two possibilities. Either there is no charge, Q is equal to 0, or the value is pi. Similarly, torque will be PE when the angle between this P and E is minus pi by 2. So the restoring torque should be T minus Q is equal to T plus Q. We can also calculate potential energy using this. We know that the potential energy is equal to work. if work done by the system, that is minus W. So by using this, we can also calculate the energy. The energy with W can also be written as tau d theta and or PE sin theta d theta. In place of tau, you can use PE. So this will give you the PE cos theta. So your energy is minus PE. So the energy is 0 for plus minus pi by 2 and maximum for pi and minimum for 0. Now the interesting thing is the torque is maximum, then the energy is 0. When the energy is maximum, the torque is 0. Here we have something for studies. In the sketch, a dipole is free to rotate. We have shown A, B, C, D, E, 5 dipoles. Field is from left to right. Which orientation has the smallest potential energy? This is asked. Smallest potential energy. We have shown, we have discussed here in the previous chapter, previous slide, that when it is maximum, maximum. The energy will be smallest when the torque, there is no torque, or the dipole is in the direction of the electric field. So that nothing change, no change will be observed. You will have a smallest. If the charge, the dipole is in opposite direction, you will have maximum potential energy. Solve these on the paper and analyze. Here I have given some examples of electrostatic fields. In copper wire of household circuits, we have the electrostatic field of about 10 to the minus 2 nano per coulomb, Newton per coulomb. In a comb, when you do this, this is of 10 to the 3 Newton per coulomb. So in the cool comb we have very high. If you want to study more electrostatic field than this, then it is inside a TV or computer picture tube. Then you have 5 Newton per coulomb. Near the charge drum of photocopier have to do 5. Same. The breakdown E field across the air gap is roughly 3 into 10 to the power 6. The electric field at the electron's orbit is 5 to the 10 to the power 11, and the surface of uranium it is about 3 into 10 to the power 21. Just to give you information I have put here. In this lecture, we have studied the torque, the meaning of torque, and the expression for torque in an electric field. We have also discussed the basics of energy, potential energy. Many applications we have for the torque. Torque can move the dipoles, and by this motion the energy can be stored or dissipated. So many applications are there. Thank you.